We're going to do a little bit of vocab today and then some practice problems, and then I have a quizzes for us, and we're going to call it a day. Just to keep myself reliable on time, this period ends at 9:40, so perfect. All right, so a rational function is any function that can be written as a ratio of two polynomials. So first, let's write down the definition, and then then I'll show you some examples. So let's just write down what a rational function is. The whole unit is around these things. So a rational function is any function, that can be written as a ratio of two polynomials. So any function that can be written as a ratio of two polynomials. That's what a rational function is. So what the general form would look like is where I have a function f of x, and that's equal to p of x over q of x, where p of x and q of x, I have two functions, p of x and q of x, I don't know what they are yet, where they are polynomials. So really it's where I have a fraction with a polynomial on top and a polynomial on bottom. And I'll give you more specific examples in a second. But a rational function, hold on, let me finish this word. A rational function is where I have a fraction with a polynomial on top and a polynomial on bottom. This unit goes directly hand in hand with the unit we just finished. Our polynomials. Okay, so some examples that may seem a little bit more familiar with you if we excuse these letters for numbers. So an example of a rational function would be, remember, a fraction with two polynomials, one on top, one on bottom, where I can have x to the third power minus 2x squared plus 3 divided by x squared plus 2. So I have two polynomials. We know what polynomials are. We've been working with them all last unit. Two polynomials in a fraction, one on top, one on bottom. Alrighty. A rational function can be just one polynomial. So I can have just x to the fifth power minus 2x plus 3. I could have just one of them. I also could take a polynomial and I could write it in its factored form. So I also could take a polynomial and I could have factored it and be left with x plus 2, x plus 4, and have x plus 2 on the bottom. So I could have taken a polynomial, factored it, and write it in the form of a fraction. So these are all rational functions. All of these are rationals. All polynomials are rational numbers. So you might want to write that down. All polynomials are rational numbers. All polynomials are rational numbers. That includes their factored form, because I can FOIL this out, which we did last unit. I can FOIL this out and get a polynomial out of it. I can get x squared plus 6x plus 8 out of that. So that includes their factored form. Okay? Some examples that are not rational functions, some things that are not rational is, let's see some specific examples. When we have a fraction, but what we don't like, we have a polynomial in the denominator, the bottom, but the issue here that makes it not rational is we can't have any radicals. So remember, this square root is a radical. You can't have any radicals. A radical number is not a rational number. No radicals. So the square root of any number is not the square root of x would not be good. Another example that's not a rational function would be if I had an exponent that had a fraction. You also can't have a fraction as an exponent. No fractions as exponents. We can have exponents, but they can't be fractions. No fractions. Let me move this over so I have more room. No fractions as exponents. Okay, and lastly, one last example is we cannot have you also can't have any variables as exponents. No variables as exponents. So no letters. The only thing we can have as exponents is nice whole numbers. Okay, so those are just examples of some rational versus irrational, which means not rational functions. Okay, any questions so far? This whole unit will be working with rational functions. That's the name of this unit. So getting a little more specific, we're going to dive really into, that's the general idea of what a rational function is. We're going to dive into the different characteristics about rational functions. Rational functions are going to have what we call asymptotes. And whether you have heard about asymptotes or not, I will teach you them. We have both horizontal and vertical asymptotes, and we've talked about the difference between horizontal and vertical before. But a horizontal asymptote, again, we'll write it down, and then I will show you examples in the pictures below. But first, let's write down these vocabulary words. It's very important that you know what horizontal and vertical asymptotes are, though. Today, we're going to focus on horizontal asymptotes. Tomorrow, we're going to practice on vertical. So we're going to spend 2 whole days on each of these. So a horizontal asymptote is a horizontal line that gets closer and closer to a number but never touches it. So let's write that down. A horizontal asymptote is a horizontal line that gets closer and closer to a number, but never touches it. And then I'm just going to write myself a note just in case you're not ever sure which way is horizontal. Horizontal is the left to right way. So a horizontal asymptote is a horizontal line that gets closer and closer to a number but never touches it. Again, you're like, okay, not really sure where she's going with this, but all right, I'll go with it, Ms. Bishop. I'll show you an example here in just 1 second. All right, and then a vertical asymptote is going to be exactly the same thing, but it's going to be a vertical line that gets closer and closer to a number but never touches it. So let's write that down. A vertical line, it's the same definition, but switch horizontal for vertical. A vertical line that gets closer and closer. Whoopsies. Closer and closer to a number, but never touches it. And then I like to write myself a note that vertical means going up and down. All right, so finish writing that down and then I will show you what we are talking about in the examples below. Take about 10 more seconds and finish that. Alrighty, so one thing I want to let you know about rational functions that's different. So we're going to see a lot of similarities from this unit to last unit. Like for an example, next week we're going to do end behavior again. And then we're also going to do next week domain and range, increasing and decreasing. And you're like, okay, what's different from this unit? From last unit we had functions that were all one thing. Last unit we had something that looked like that. This unit, all of our functions that are rational functions are going to look something like this. They're not that much different, but I have something that goes, my graph goes like this and my graph goes like this. I have two separate graphs that are being separated by asymptotes. So that's what this big asymptote is. Alrighty. You're right now, you're like, how am I ever going to know how to do domain and range of that thing? We'll do it one step at a time, and there's a lot of similarities to what we've already done. But I'm just letting you know, one of the big differences from last unit to this unit is what the graphs are going to look like, and that's okay. So this is where my graph is. This green thing is my graph. That's now highlighted in pink, but I'm going to erase it. But I'm just letting you know, the green thing is my graph. Here are, I'm going to highlight it, but then I'll erase it. Here are my X and Y axis. And so the question says, find your vertical and your horizontal asymptote. So my vertical asymptote and my horizontal asymptote. VA for vertical asymptote and HA for horizontal asymptote. So vertical asymptote means what number going up and down is my graph getting very, very close to but never touching. So you're going to look at the ends of your graphs. So the ends of my graphs going up and down. So here's one of my graphs. And my graph starts to go vertical. I hope you agree with me that my graph starts to go vertical around over here, right? My graph is horizontal around here. And then starts to go vertical over here. Vertical means up and down, right? So my graph starts to go vertical over here. And this graph goes on forever, just like all the other graphs that we were using. It goes on forever. And if I were to extend this line, it would get closer and closer and closer to this number over here, but never actually touch it. That's a vertical asymptote. This line right here, this green graph is getting closer and closer to this number. It's fastly approaching this number, but never touching it. And that number that it's fastly approaching is 0. So I have a vertical asymptote at x equals 0. Vertical asymptotes always are x equals because they're on the x-axis. And your asymptotes should be the same whether I looked at this part of the graph or whether I looked at this part of the graph. So if I'm looking at the top part of my graph over here, if I look at the top part of my graph, I see that my graph starts to go vertical. It starts to go up and down over here on this part. And I see if I extend this graph forever, it's getting closer and closer to this point over here, but never actually touching it. And if I zoom out, that point that it's quickly approaching, but never crossing is 0. So it should be the same no matter whether I look at this part of the graph or if I look at this part of the graph. So that's my vertical asymptote. Likewise, if I go to the part of my graph that starts off horizontally, well, if this part was vertical, then the other end of my graph would have been horizontal. This part of my graph is where it starts to get horizontal. Horizontal means left to right. I can see that my part of my graph, if I extend it, it's getting closer and closer to this number, but never actually touching it. And same thing on this side of my graph. It's getting closer and closer to this number right here, but never touching it. Well, that also happens at 0, but that 0 right there happens at y equals 0. Again, horizontal asymptotes are always at y equals a number. Vertical asymptotes are x equals a number. And if you want to put that right next to your definition, that's fine. Horizontal asymptotes, y equals the number. Vertical asymptotes are always x equals a number. Okay. Looking at graphs and pulling out asymptotes just take practice. Sometimes I still struggle with them. It just takes some practice, and you definitely will get the practice over the next few days, okay? All right. Let's go look at this one over here. Any questions? Do you have any questions? All right. Let's look over here. This graph, I don't like this graph because the asymptotes are already drawn in for you, which won't usually be the case, but I didn't make this example. I also don't like this graph because it steers you away from the fact that this right here is your, that's your x and y axis, not this part right here. This is where your asymptotes are going to be, but they're not always going to be drawn in for you, so I want to ignore that part right there, but I still want to show you. We're going to think of it the same way I just told you. So again, we want to find the vertical asymptote and we want to find the horizontal asymptote. And just to get me used to it, I know vertical asymptote is going to be some sort of x equals and horizontal asymptote is going to be some sort of y equals. I don't even know what number, but I need to get used to x equals for vertical and y equals for horizontal. All right, starting with vertical, I'm going to go to where my graph starts to hit a vertical spot. So whether you start with this graph or whether you start with this one, they're going to approach the same number. All righty, so where my graph starts to go vertical is right about here. In the chat, what number is this graph closely approaching but never actually touching? In the chat, please. What number is that closely approaching but not actually going to touch? Whether you go up or whether you go up this way. Two. Sorry, I didn't see your chat till now, but yes, x equals 2. This is closely approaching 2, but it's never actually going to touch this point of 2. This right, if you're like, how'd you know? There's a 2 right here. That's where that point is. Okay, and it's the same thing if I looked on this part of the graph. It's closely pointing there, but it's not going to touch it. Alrighty. Then vertically also, or horizontally, I'm going to go look where my graph starts to go horizontal. And this graph gets super, super close to this point, but it's never going to actually touch it, whether I want it to or not. It's not going to. What point is that graph getting really, really close to, but not going to touch for horizontal on either end? It's getting super, super close, but it's not going to touch. In the chat for horizontal, going left to right. Yes, 0. It's getting super close to the number 0, but it's not actually going to touch it. So y equals 0. Whoops. Okay. Any questions right now? Alrighty, like I said, just looking at your graph and pulling out the asymptotes is a difficult strategy, and we're going to get practice throughout this whole unit. That's not something I expect you to move on from today, knowing exactly how to do it. Okay. So we're going to move on though. So again, this is just going to come each day. We're going to build up on this skill. We are going to skip the next page. The next page it's like an intro for the page after that, but I think we can just go to the page after that. So we're going to be on page 3. If you just got here, that's totally fine. Thanks for letting me know, but please make sure you get the notes after class. They'll be posted during the lunch break. But we're going to be on page 3 now. So again, page 2, we are going to learn everything we need to for page 2 in page 3. So we're just going to skip the intro and go right to page 3. Alrighty, sometimes I'm not going to give you the graph and I'm going to just give you the equation and I'm going to say, tell me where the horizontal asymptote is. That's almost easier. For me, looking at the equation is easier knowing these properties. I would make a big star on this page. You do not need to memorize this. If life was normal and you were all in the building, you would need to memorize these 3 properties, but you are remote or you're hybrid and you're open note, that's great. But then this what was a hard concept now becomes a very easy concept and you need to utilize that. Star this page. This is an important page and you don't need to memorize it. You just need to know how to use this page. But by looking at an equation, you can know these 3 properties and you will tell me what the horizontal asymptote is. I like this better than looking at a graph. So if I give you an equation, let me tell you the 3 properties and then we will do a couple of examples. So if we have an equation that reads like this, if I have a rational function where p of x is on top and q of x is on bottom, if p of x is on top and q of x is on bottom, so if the degree of p of x, so remember that one's on top, so I'll write a note for you. If the one on top, if the degree on top is bigger, this means greater. This sign means greater. You need to know that. I always think of it as it's clapping. The greater hand is clapping for the bigger one. If it's greater than, so you can write yourself a note that it's greater than. I'm just running out of room. If the top degree, you know what the degrees are. If the top degree is greater than the bottom degree, there is no horizontal asymptote. That's your first property. Looking at the equation, if the top degree is bigger than the bottom degree, there is no horizontal asymptote. That's your first one. Okay, your second scenario is if your degree on top, again, p of x is the one that's on top, is smaller than, if it's less than, that means less than. If it's the top degree is less than the bottom one, your horizontal asymptote is equal to y equals 0. And then if the top degree is equal to the bottom degree, so top is equal to bottom, that's the easiest one to remember, but it requires the most work. Then your horizontal asymptote is equal to y equals the leading coefficient of the top divided by the leading coefficient of the bottom. So this is a lot more work than it sounds like a lot more work than it really is. So let's go do an example of all of these. Alrighty. So the question says, identify the horizontal asymptote of each function without graphing. So you don't need to graph these. You have your 3 properties and you have an equation. Sorry, my phone is dying a slow death in the classroom. I'm not sure what's going on. Alrighty, so you're going to look at the property, or you're going to look at the degrees of both the top and both the bottom. So the top here, degrees are exponents. So I hope you agree with me that the top of this fraction has an exponent of 0. Remember, only things that have variables or letters have an exponent. So that doesn't have a letter with it, so there's no exponent. So that has a degree of 0. This has a degree of 1. You guys are good at degrees. Don't forget everything you just learned. Remember, any letter that has no exponent has an exponent of 1. That doesn't mean that's the fraction. 0 divided by 1 is not your answer, but now we know that the bigger number's on the bottom. So I need to match this to a scenario that I have. So the top number is less than the bottom, right? My degree of 0 is less than the degree of 1. So that means the top is less than the bottom. This is the scenario that I have at play. So since the top degree is less than the bottom degree, my horizontal asymptote, which is what the problem says to find, is equal to y equals 0. That's all you need to do. Okay? Because the top was less than bottom. Okay. For showing your work, I want you to tell me what type of rule you use. The top was less than bottom. The top is equal to the bottom. The top is greater than the bottom. I want you to tell me which one you used. Okay. Let's do part B. Part B says, part B has a degree of, well, I see that I have the degree, the highest degree. We're always going to take the highest degree, you guys. I have 4x to the first power, right? Anytime you have an x, it has an exponent of 1. So this has a degree of 1. And the bottom has a degree of 1. So the scenario that I have here, being played is that the top is equal to the bottom. If the degree is 1 on top and the degree is 1 on bottom, the top is equal to the bottom. And so when that happens, I'm going to read the rule. It says your horizontal asymptote is equal to y equals the leading coefficient. Remember, your leading coefficient is the number in front of the variable. The leading coefficient on top divided by the leading coefficient on bottom. So the leading coefficient on top is 4. That's the number in front of the variable. And the leading coefficient on bottom, in the chat, what is the leading coefficient on the bottom? In the chat, what's the leading coefficient on the bottom? 1. Good. When there is no coefficient, there's a 1 there. 4 divided by 1 is just 4. So my horizontal asymptote is equal to y equals 4. Okay. Not too bad. Alrighty, let's keep going. The degree on top. What's the degree on top in this one right here? In the chat, what's the degree that's on the top? 0, right. When there is no variable, when there's no letter, there's a degree of 0. There's no x on top of this fraction. Okay. What's the degree on bottom? You take the biggest degree you see. What's the degree on the bottom? Two. Thank you. I'm quiet today. Alrighty, so I have the degree is bigger on bottom. So the degree is bigger on bottom. That would put me in a scenario where the top is less than the bottom. So if the top is less than the bottom, then I'm at the middle again. So top is less than the bottom. So that means, just following the rule, my horizontal asymptote is equal to y equals 0, just following the rule. Alrighty, and then my last one, I have a degree of 2 on top, and I have a degree of 1 on bottom, right? Anytime there is no exponent, there's an exponent of 1 there. So the bigger degree is on top, so the top is greater than the bottom. And then that would mean top is greater than the bottom, puts me at my first scenario, which is there is no horizontal asymptote. So you can write there is no horizontal asymptote. That's a lot of work. So I'm going to put horizontal asymptote as if I was writing the answer, and then I'm going to write none. Okay.